Welcome again to this presentation. Today we are going to discuss the question and the answers in thermochemistry. Last time we ended on question 61. Today we are starting question 62. Question 62 is saying, how much work is required to compress 7.5 moles of iod gas at 400 Kelvin from 5.2 to 2.1 liter? And they're asking, what is the change in internal energy of the gas? What is the change in the internal energy of the gas? They're also asking how much heat will be transferred to the process. How much heat will be transferred to the during this process. Let's see the answer. Here the temperature is constant. We have a constant temperature 400 Kelvin. The temperature is constant, and here we don't have a constant external pressure. We consider that we have the reversible process. We have a constant temperature, and we consider that we have the reversible process because we don't have the constant external pressure in the question. Some of the formulas that we can use for calculating the reversible process when the temperature is constant. In that case, we can use this one, which is equal to minus N as a constant, the temperature, which is constant, the Ln V2 over V1, the final volume over the initial volume. We can also use this one, which is equal to negative 2.303 times the number of moles, the gas constant, the temperature, logarithm V2 over V1. We are using this one, but we have other formulas which can be used to calculate the work done in the reversible process at constant temperature, like this one, for example, and this one, for example, and the other formula that can be used when we are looking for other parameters. For example, this one, the one we have selected, the one we have highlighted in black, you can see it has the final volume and initial volume that were given the question. Have the compression from 5.2 liter to 2.1 liter. That means we have the initial volume and we have also the final volume. You can use this formula and this formula. The other formulas, like for example this one, we use them when you are having the initial pressure and the final pressure. And this one, we can when you have the one volume, you can find another volume, and when you have another one pressure, you can find another pressure. Let's use this question then to calculate the answer. I told you that the temperature is constant. The temperature is constant. The change in the temperature is 0. The delta T is equal to 0. And you know that the du, which is the change in internal energy, is equal to NCV dt. That means because the dt is equal to 0, we have also the change in internal energy, which is 0. The change in internal energy is 0. We can replace 0 here. After replacing this internal energy of 0, we get 0 is equal to the Q, which is the heat, plus the work done. That means the heat is equal to negative work done. And let's find the work done, because here they are asking how much work is required. How much work is required? Let's first calculate the work by using this formula. The work required is equal to negative N. This is the number of moles. We have 7.5 moles, the number of moles, times the gas constant, times the temperature, which was given as 400 Kelvin times the Ln, the 2.1 over 5.2. Because we have the V2, which is equal to 2.1, the gas is compressed from V1, which is 5.2, to V final, or V2, which is 2.1. After doing the calculation, then we can get the work done is equal to this value, and the heat is equal to the Q is equal to negative work done. That means the Q will be equal to negative the work done, this negative this value. What does it mean? Here, the work done is positive. During isothermal, the constant temperature, the compression, it should be constant temperature. And if you are compressing the gas, they are going to the temperature is going to increase. And for you to keep the temperature constant, you should remove some heat. And that is the reason why this heat is negative. That means the heat has to be removed so that the temperature remains constant. And for this work done has to be positive, because the work is done by from the surrounding to the system. So the system is gaining the work. That is what we asked in this question. Calculate the work done, we have it. The work done, we have it. And then how much heat, we have also the heat in this answer. Let's go to question 63. Question 63 is asking, we have 3.2 moles of a gas expanding from 5 atmosphere to 1.4 atmosphere. Here we have the initial 5 atmosphere to 1 atmosphere at constant temperature. We have a 3.2 mole of gas expands from a pressure of 5 atmosphere to 1 atmosphere at constant temperature of 127 degrees Celsius. They are asking, is the work done by the gas or on the gas? Is the work done by the gas or on the gas? And remember, we have an expansion from 5 atmosphere to 1 atmosphere. Then they're asking how much energy was transferred by the work and the heat. How much energy was transferred by work and the heat. Here, what we need to check is whether we are having reversible or irreversible process, because here we know that we are at constant temperature. We have isothermal process. We are at constant temperature, but do we have the constant external pressure? Here, no, we don't have the constant external pressure. That means we have the reversible. We'll use the formula for isothermal reversible process to calculate the work done. Because they're asking, is the work done by the gas or on the gas? Of course, we have the expansion. And when you have the expansion, the system is doing the work, and in this case, the work done should be negative, because we have the expansion. The system is doing the work. Now we have the final. We have the final pressure. This is the final pressure, and we have also the initial pressure. Here we don't have the volumes, but you have the initial and the final pressure. That means this formula, we don't use it. This one also, we don't use it, but we can use this one where we have the initial and the final pressure. So the work is done by the gas. So the gas is expanding, like I was explaining to you. It is an expansion. That means the system is doing the work. The work done is negative. What they're asking is the work done by the gas or on the gas. So the work is done by the gas. The gas is expanding. We know that the temperature is constant, and when the temperature is constant, delta T is equal to 0, the internal energy or the change in internal energy is also equal to 0. NCV, because the dT, the change in temperature, is equal to 0. That means the internal energy will be equal to 0. That means also that the heat is equal to minus work done. Q is equal to negative work done. Let's use this formula to calculate the work done. The work done is equal to negative the number of mole times the gas constant times temperature, ln P1 over P2. Here we have the number of mole, 3.2 moles times the gas constant times the temperature times the ln of the ratio of P1 over P2. And the P1 is 5 atmosphere and the P2 is the 1.4 atmosphere. After calculation, we get the work done is equal to this value, and it is negative because we have the expansion and because the system is doing the work. And you can calculate the heat. The heat is equal to negative work done. So the heat is positive. Heat is positive because expansion, if there is an expansion, there is a decrease in temperature, and for you to keep the temperature constant, you should supply the external heat to the system, because isothermal process is a constant temperature, and if there is an expansion, there is a decrease in temperature, and to have the constant temperature, you should supply the external heat. Let's see question 64. Question 64 is saying calculate the heat, calculate the heat, calculate the heat, calculate the work done, calculate the internal energy, and calculate the enthalpy when 2 moles of a gas are expanded reversibly isothermal. That means we have a reversible isothermal process from 10 atmosphere to 5 atmosphere at 27 degrees Celsius. Here we have a reversible process which is isothermal. We can use the formula to calculate reversible isothermal process. Work done to calculate the work done in the reversible isothermal process. Here also we have the pressure, the initial pressure, and we have the final pressure. Let's see the formulas to calculate the work done. We'll use this one because we have the initial pressure and the final pressure in the equation. We will not use this one or this one because we don't have the initial and the final pressure. So you can use this one, or you can also use this formula. So let's see how the work done is calculated. We have explained that the dT is equal to 0 when you have isothermal process, the constant temperature. We will change this temperature to Kelvin. That means we add 273 to this temperature. So here we know that the Q will be equal to minus work done, because the du is 0, because the change in temperature is 0. We have a constant temperature. What is the enthalpy? The enthalpy is equal to NCP dt, because we were asked to calculate the enthalpy. The internal energy is equal to 0. What is the enthalpy? Enthalpy will be equal to 0 also, because it's equal to NCP. Enthalpy is when we have constant pressure. When you have the NCP dt, in this case, dt is equal to 0 because we have constant temperature. In this case, the delta H or enthalpy will be equal to 0, and the internal energy is also equal to 0. And remember, the internal energy is the NCV dt, and the enthalpy is the NCP dt. Can you see their difference? This is at constant volume, heat capacity at constant volume, and here this is the heat capacity at constant pressure. So you should be able to differentiate them. But at constant temperature, all of them they are equal to 0 because the change in temperature is equal to 0. The change in temperature is equal to 0. Let's calculate the work done by using this formula. So we can calculate the work done. The number of moles was given as 2 moles times the gas constant times the temperature. The temperature, this is 27 plus 273 because we are changing it in this 27 degrees Celsius to Kelvin, then times the Ln 10 atmosphere, 5 atmosphere. That is the P1 and the P2. Then after calculation, we get the work done is equal to this value. You can see the work done is negative because we have an expansion. The gas is expanding. And what about the heat? The heat will be equal to negative work done. The heat is equal to negative work done, and it will be positive because expansion is a decrease in temperature. For you to have the constant temperature, you should supply the external heat so that the temperature stays constant. Let's see question 65. Question 65 is saying 2 liters of nitrogen. We have the initial volume, 2 liters of nitrogen at 0 degrees Celsius. We have 0 degrees Celsius initial temperature. And 5 atmosphere. We have also initial pressure are exploded isothermal. That means we have the constant temperature against a constant external pressure of 1 atmosphere. You have also a constant external pressure. If you have a constant external pressure, that means you have irreversible. That means you have irreversible isothermal process because you have a constant external pressure. When you have a constant external pressure, that means in this case you are having the irreversible isothermal process. Irreversible process because you have a constant external pressure and we have a isothermal process. Is the isothermal? The question they are saying isothermal. That means it is the isothermal process, a constant temperature process, and here we have the irreversible because we have the constant external pressure. In all question where you will see the constant external pressure process, in this case is the irreversible. They are saying until the pressure of the gas reaches 1 atmosphere, and they are asking calculate how much heat will be absorbed or released by the system. Let's see the formula now, which are used for irreversible process when we have isothermal. We have irreversible process and we have isothermal process. That means the work done is equal to negative 2. Like we have seen, the work done is equal to negative the heat, or the heat is equal to negative work done. In irreversible process, when you have isothermal process, you can use this formula where you have the external pressure. It was given as 1 atmosphere, constant external pressure, the V2 over V1. Then V2, do we have it? But V1, we have it, is 2 liters. We can also use this one when you have the pressures, when you have P1 and P2. Because here we have the 5 atmosphere, that is the P1, are exploded until the pressure reaches 1 atmosphere. That is the P2 also was given. So we can use this for this formula. But do we have the number of moles? We don't have the number of moles. You can calculate it by using PV is equal to any other and calculate the number of moles and replace the number of moles here. And what about this one? We have the 2 liters. This is V1, but we don't have a V2. We can calculate a V2. So we can use this one by calculating the V2. Let's first calculate the V2 by using this formula P1 V1 is equal to P2 V2. That means V2 over V1 is equal to P1 P2. Here we can have the formula. So P1 V1, P1 is 5 atmosphere, the V1 is 2 liter, then P2 is 1 atmosphere, and the V2 we need to find it is unknown. Find V2 is equal to 10 liter. After finding V2, then we can calculate the irreversible work done by using the formula. The external pressure here is negative external pressure. That means negative 1 because the external pressure is 1 atmosphere. Then the V2 10 liter minus V1, which is 2 liter. In this case, we do calculation and we see that the work done is equal to negative 810 joule by using this formula. I told you that you can also, because they have calculate how much heat will be absorbed or released. Here is the heat. What will be the heat here? That means the heat will be negative work done, it will be positive. That means the heat is going to be absorbed because it is positive. If you check in the question, they are saying they are exploded isothermally against constant external pressure of 5 atmosphere. And if you check, we have the 5 atmosphere, which is the initial pressure, and you have the final pressure, which is the 1 atmosphere. That means you have an expansion. If you have an expansion, the pressure is going to decrease, the temperature is going to decrease, and because it is isothermal, for you to get the constant temperature, you should supply the external heat. That is only why the heat here will be positive 810 joule. So the heat is absorbed. We can also use this formula, because we are having the initial pressure and we have the final pressure until the pressure reaches 1. We have the final pressure. We can calculate the number of mole first and then use this formula. So PV is equal to nRT. That means the number of mole is equal to P times V over RT. The pressure 5 atmosphere. The volume is 2 liters. 2 liters of nitrogen gas at 0 degrees Celsius and at 5 atmosphere. That means 5 atmosphere. The volume 2 liters. The gas constant, we use this one 0.08206 liter atmosphere per mole Kelvin, because we have the pressure in the atmosphere. Then times the temperature is 0 degrees Celsius, which is equal to 273 Kelvin. After getting the number of moles, then we can use this formula to calculate the work done. So you can replace the number of moles, the gas constant, the temperature, and use the formula, and here we replace the P2 and P1. After using this formula, we will see that the work done is equal to this value, and the heat will be equal to positive, and the heat is absorbed, is an expansion. The temperature decreases during expansion, and for a system to keep the same temperature, heat must be absorbed. Here, the heat must be absorbed. The system is absorbing the heat so that the temperature stays constant. Let's move to question 66. Question 66 is asking, we have 6 moles of anhydrous gas, which is expanding isothermally from 1 liter to 10 liter, expanding at constant temperature, isothermally from 1 liter to 10 liter. Calculate the maximum work done by the gas. Here, we need to calculate the maximum work done. And we don't know whether it is reversible or irreversible, because we need to check in which way do we have the maximum work done. And you have seen that we need to calculate the maximum work done. And remember, we have seen that the magnitude of work in reversible expansion is more than the magnitude of work in irreversible expansion. In other sessions, we have seen that the magnitude of work in reversible expansion is more than the magnitude of work in irreversible expansion. That means where we have the maximum of work is in reversible process. Reversible expansion process, that is where we have a maximum work than when you compare irreversible process. When you have reversible expansion process, that's why you have the maximum work than when you have irreversible expansion process. That means the formula that we'll be using here, they are the formula for reversible. And what do we have here? We have isothermally from 1 liter to 10 liter. That means you have the volumes, the initial volume and the final volume, and the constant temperature. So we use this formula where you have the volumes. Let's replace the values. We have 6 moles. We have 6 moles. The gas constant times the temperature, and then ln 10 liter over 1 liter. That means this is the final volume and the initial volume. In this case, we see that the maximum work done will be equal to this value. The work done is negative because we are having the expansion.